Let's just wait for a couple of more minutes and then we'll start. Hello everyone, this is Tanya. I'm one of the TAs assigned to the aircraft design course taught by Professor A.K. Ghosh. So today we'll go over the questions of week 6 and then cover some questions that will help us solve the week 7 assignment. Okay, so let's start. This was the question from week 6 assignment. Which of the following option is not correct? So a high wing contributes to lateral instability and longitudinal stability. Airplane with higher wing loading has lower stall speed. A low wing contributes to lateral stability and longitudinal instability. All of these. So let's look at the second option. Airplane with higher wing loading has lower stall speed. Is that true? So what was the equation for stall speed? We stall was under root 2W by S by rho CL max. So if you have a higher wing loading, it has a higher stall speed, right? It's directly proportional to under root, but it's directly proportional. So this statement is untrue. They've asked you for not correct, so fine. And as far as low wing and high wing configurations are concerned, we've discussed their lateral stability and instability quite a few times. Let's just briefly go over it. So when a high wing configuration is subjected to a gust, the oncoming velocity impinges here. Sorry, let me just erase this. Okay, not able to erase it. Okay, let's just see. When a high wing configuration rolls here, so there's a component of velocity that acts in this direction, which contributes to a restoring moment. Similarly, when it's a low wing configuration and it rolls in the similar direction due to gust, there is a normal component of velocity acting in this direction, which further contributes towards destabilizing the motion. There is no restoring moment. So high wing is lateral stable, lateral contributes toward lateral stability, and low wing contributes towards lateral destabilizing, right? Laterally destabilizing. Now, what about longitudinal stability? Can someone tell me whether the high wing and low wing, what is the difference when it comes to longitudinal stability? So lateral we understood. So both these statements are in fact wrong. And you can see that with respect to high wing contributes to lateral stability. It's not instability. But can we discuss about longitudinal stability and instability? Can someone tell me what they think? Like which configuration would benefit the longitudinal stability or instability? Can you tell me? Can anyone just try? Well, let me just try to figure out why I'm not able to erase this. Can you just think about the uh, longitudinal stability with respect to high and low wing? Okay, can someone just tell me? Either type it down or just let me know. Meanwhile, I'll figure out why I'm not able to edit this. Can someone try? Can someone tell me? Is the high wing, so high wing, lateral case, longitudinal case, low wing. So lateral case, high wing is stable or unstable? For the lateral case, is the high wing configuration stable or unstable? Am I audible? Can someone confirm if I'm audible? Okay, so yes, lateral case, this is stable, correct. And what about the low wing? Low wing would be unstable. Now tell me about the longitudinal case. High wing stable or unstable? High wing unstable, okay. And low wing stable. Can you tell me why? So longitudinal case is the dynamics about which axis? The longitudinal axis. So what is the angle that you would analyze there? For the longitudinal stability, what angle dynamics would you? Not alpha. You cannot control alpha, right? So alpha is the angle that the oncoming velocity makes with the fuselage reference line or the mean chord line. So you cannot really control alpha. What angle can you control? When we studied longitudinal stability, which angle did we consider? So it's the pitch dynamics, right? Pitch up and pitch down. Okay. Now, can you tell me, you told me correctly that the high wing configuration is longitudinally unstable. Can you tell me why? So let's just draw the configuration. So this is your fuselage reference line and your high wing is like this, okay? And your CG is here. This is your CG. So can you try, what are the aerodynamic forces acting on this wing or the aerodynamic forces that the wing produces? What are the forces? What are the aerodynamic forces that's acting on the wing? Lift, drag, and pitching moment. Okay. Just the forces? Okay, fine. Let's just go lift, drag, and let's assume that it is symmetric airfoil, so you have no pitching moment. Okay, so now can you tell me why this high wing configuration is unstable? So is the if your aircraft has just a wing, is it stable? If your aircraft has just a wing, is it stable? Unstable. Why is it unstable if it is just wing? Wing is a destabilizing component, yes, but why? So what is the component that stabilizes? In the longitudinal case, wing alone configuration is unstable. It creates pitch up moment. Okay. Okay, fine. So if your aircraft is subjected to a gust and your wing is providing a lift, it provides a destabilizing moment about CG. Correct, it creates pitching moment. So what in this high wing configuration contributes towards further instability? So this lift, when it acts about the CG, it produces a further, suppose it's subjected to a gust, okay? So it's subjected to a gust and you have an alpha here and your lift contributes towards further destabilizing moment. What about drag? Does the drag create stabilizing or destabilizing moment in this configuration? So here lift produces pitch up, exactly. Both lift and drag give you pitch up moment, so both are destabilizing. Now look at the low wing configuration. So you have fuselage reference line, same CG location. You have a low wing here. You have lift, drag, and again assume it's a symmetric airfoil. So the lift again produces destabilizing moment. What about drag? It produces a stabilizing, restorative moment. So the low wing configuration is more stable when compared to high wing configuration in the longitudinal dynamics. Okay, so low wing is more stable for longitudinal dynamics, longitudinal stability. Okay, so this is why all these three statements are incorrect. So all the above are incorrect. Okay, let's go to the next question. With the increase in wing loading, the corner velocity of an airplane will, so all kinds of velocity, so V stall or just simple V, they are all directly proportional to under root of wing loading, right? This is remaining constant. So with the increase of wing loading, corner velocity or any velocity will increase, right? So directly proportional. What is corner velocity? What is this corner velocity? You've all solved the assignment, so you might have gone over this concept. What is corner velocity? We did do this in airplane performance. So what is corner velocity? Velocity of maximum load factor, where load factor and CL have maximum value. Yes. So in the VN diagram, you remember this VN diagram, the velocity, just a minute. So velocity at this point is called corner velocity. So along this curve, along the curved lines, what is the, so this VN diagram shows you the limits, okay, the loads, the maximum uh, limits that the velocity can take. So the curved line signifies what load, what limit? Both the curves, the upper and the lower curves, what limit do they impose on the velocity? So you are right. So where the load factor and CL have maximum value, it's at this point, right? Load factor is maximum throughout this line. Load factor is N. So N max happens throughout this line. And CL max also happens at this point. So what can you say about the curved line? What limit does it impose on the velocity? This N max corresponds to structural limit, right? So when you do your maximum G maneuvers, you encounter this N max, right? So max G maneuvers. That is what is this N max, right? What is this curved line? What limit is that? This is the maximum velocity that the aircraft can sustain because of the structural limits. What about the curved line? Max CL. So what is the velocity corresponding to max CL? What is that case? V stall, exactly. So this is positive stall and this is negative stall. These are the limits, the curved lines. The upper curve is the positive stall limit. The lower curve is the negative stall limit and the line is the structural limit. So this is the equation for your corner velocity where N is max. right? Everything else is similar to the typical velocity equation, but where n is max, you have this n max term added here. But either way, it is directly proportional to under root of W by S, proportional to under root of wing loading. And hence the answer is increase, okay? Okay, let's go to the next question. Which of the following option is not correct? Velocity at minimum power and velocity at minimum thrust are the same. Are they? What about the other three statements? The equilibrium, at equilibrium, net moment about CG is 0. Is this true? Okay, let's go one by one. The first statement, is it true? First statement, velocity at minimum power and velocity at minimum thrust. No. No, not true. Second statement, equilibrium, at equilibrium, net moment at CG is 0. Second statement, at equilibrium, net moment about CG is 0. True. Yes. Airplane with higher wing loading has higher stall speed. Yes, we just saw this. At aerodynamic center, pitching moment coefficient remains constant irrespective of angle of attack. This is true by definition. That is the definition of aerodynamic center, right? This is true. So only this statement is untrue. So can you tell me what the velocity at minimum power and velocity at minimum thrust are? What is the equation? Velocity at minimum thrust. Can you tell me what they are? What the values are? I think we discussed this in the first two week lectures. Just quickly derive it and tell me. Just remember the equations for CL at both these conditions and then plug it into your typical V equation. V equation is under root OW by S rho CL. So this CL will change for minimum power and minimum thrust. Just recall those equations and tell me what VMP and VMT are. What was CLMP? And CLMP. What is CLMP? Can you tell me that equation? Just refer your notes and let me know. CL for minimum thrust is under root of CD naught by K. It's not just CD naught of K, okay? So it's CD naught by K. And what about minimum power? Under roots 3 CD naught by K, correct. So when you plug it in, you get equations. Just change the CL here and you get two different values of velocity. So velocity of minimum power and velocity of minimum thrust are not the same because CL is changing, okay? Okay, so these are just the equations, the table that we had seen in the first week. Okay, the wing loading for an airplane is 50 kg per meter square and maximum lift coefficient is 2.4. Find the stall speed. It's very simple. This equation we've been seeing right from the beginning. So what was wing loading? To 50, it's given in kg per meter, so 9.81. Density is 1.225. And single max is 2.4. What is this value? What is the value? Just recalculating it. Correct me if I'm going wrong somewhere, okay? I'm so getting 18.67. Okay, what if it had asked you to find the takeoff velocity? What is V takeoff for the same case? Yes, this is 18.267 meters per second. What about V takeoff? If they had asked you to find out V takeoff, how would you find it? It's 1.1 to 1.2 V stall, yeah. So you can just multiply that and find out. Okay, next question. An aircraft is flying with a wing loading of 50 and a maximum CL as 2.4. If the density is 1.225 kg per meter cube, then find takeoff velocity of the aircraft. Yeah, so this is that question. Oh, what about takeoff velocity when they've given you takeoff? Okay. If thrust to weight ratio of an airplane is 0.1 and the aerodynamic efficiency is 10, then the approach angle of the airplane will be. It's very simple, right? It's a straightforward equation. Approach angle sine theta A is 1 by L by D. So L by D minus thrust loading, right? So just plug in the values. In this case, which is 1 by 10 minus 0.1, which is 0. So approach angle is 0 degrees. Okay, okay. Now let's look at some of the questions that will help you solve the next assignment. If thrust to weight ratio increases, then takeoff distance of aircraft will. What was the equation? Do you remember the equation? If not, do you remember how to derive it? Just take a moment and tell me. Just recall the equations and just take a moment and tell me this. Decreases. Okay. What was the equation? This S liftoff. Oops. So S liftoff, what was the equation? Do you remember the equation? You're saying decreases, but how? Can you tell me what is the equation? Okay, and we'll just go over briefly how Sir had derived it in the lectures. So you just take the free body diagram of the aircraft and you have lifts, you have weight acting downwards, you have thrust, you have drag, and then you have the frictional force. So that is mu r by r. And then you take summation of forces. In the vertical direction, it is lift. Oh, there's also a reaction force here. So lift plus r equals w. In the horizontal direction, it is F equals m dv by dt, or mass into acceleration, equals thrust minus drag minus mu r into r. And you can substitute the value of r from here, right? And what do you finally get? And you take v square minus u square is equal to 2as. Take u square as 0 because you start at 0 and find out this s. S is nothing but s liftoff, right? So what do you get? You get v square by 2a. A comes from here. So this is ma is equal to t minus d minus mu r into w minus l, correct? So plug that in here and you get s liftoff. So the final equation that you get is, does anybody remember? You don't need to remember exactly, but you have to remember what it's proportional to and what it's inversely proportional to. So it's approximately equal to 1.44 W wing loading by G rho and thrust loading. Am I missing some term? Yeah, this is CL max also, right? Is this correct? Am I missing some term? Okay. So what you need to remember is this lift off distance is directly proportional to wing loading, inversely proportional to thrust loading, inversely proportional to CL max. So deflection of flaps, all of them come in this area, inversely proportional to density. Yeah. So you need to remember this, right? I think all of the questions in week 7 are based on just these relations. Even if you don't remember the equation correctly, you need to remember what it's proportional to. And if you don't remember that, just remember how to derive it, okay? So this is important. You need to remember this. Okay. The load factor of an aircraft during transition phase of takeoff maneuver will be takeoff maneuver, pull-up maneuver, anything during the transition phase will be greater than 1. So during the transition phase, you need to have lift greater than weight, and the load factor is lift by W, so it will be greater than 1. Correct? Okay. Next. Okay, takeoff distance is related to thrust as we just saw this. Is it directly proportional, inversely proportional? A, correct. So you saw that the takeoff distance was inversely proportional to 1 by thrust loading, right? So thrust is inversely proportional. Next. As the flap is deflected during landing, the ground roll distance will be ground roll, takeoff, they have the similar equations, just the forces will be reversed, but it's the same thing. So as the flap is deflected during landing, the ground roll distance will be, yes. So when you deflect the flap, your CL max increases. And we saw that CL max is ground roll distance is inversely proportional. Okay, so yes, as you increase CL max, your ground roll distance reduces. Which of the following is the correct takeoff parameter? It's a direct equation that is given in the lecture. Which is the right answer? Which is the right one? Again, it's similar to your previous. Exactly, it's directly proportional to wing loading, inversely proportional to thrust loading. So it's just, it follows the same pattern. Okay, so, takeoff parameter and takeoff distance. Okay, so this is the right answer. Just remember that it's directly proportional to wing loading, inversely proportional to thrust loading, and the CL, it's also inversely proportional to CL. Okay. Now let's do a series of questions for which the data remains same. This data would remain same for like some 2-3 questions. So just read the question carefully. For a propeller-driven aircraft with plain flaps, mission requirement data is given below. Vmax is 75 meters per second. Takeoff distance is 300 meters. Rate of climb is 7.62 meters per second. Vstall is 25 meters per second. And then you have these other parameters that relate to the airfoil, Oswald's efficiency factor, aspect ratio, and so on and so forth. Which of the following can be a tentative value of wing loading during stall? Okay, you should be able to do this. It's an easy question. So take a couple of minutes and then we'll do it together. Okay, try doing this. Wing loading during stall. Have you been able to do it? Okay, tell me how to proceed. They've asked you to find the tentative value of wing loading during stall. How do we proceed? How do we start? How do we start? What equation comes to your mind when we say stall and wing loading? Vstall. So what is the equation for Vstall? What is the equation for Vstall? We just did this. Under root of 2 W by S rho CL max. And they've asked you to find this W by S. So you have all the other terms, right? So you just have to do W by S is rho CL max by 2 into V stall square. Can you tell me the answer now? This was very simple. Why weren't you able to do it? Just try doing it now. The equation is on written there, right? So just substitute the values and tell me the answer. Option B. Okay. Can you tell me what values you've gotten? Is anybody else getting a different answer? Okay, let's just do it. So they've asked you to take sea level conditions. So 1.225 CL max. This is what they've given to you. 0.9 into 1.4. So why is CL max and the small CL max? Why are they different? Why is this different from this? Why is there a 0.9? Why is it, what is accounting? What is it accounting? Why are those two CL max different? Correct. So this is for the 2D airfoil and this is for the 3D wing. Because that is what that 0.9 factor is coming. Okay. So by 2, V stall is 25. And you get, what do you get? You get 482.3. You get it in Newton per meter square. The answers are given in kg per meter square. So you divide by 9.81 and you get 49 point something around that range kg per meter square. So yes, second option is right. Okay, is this clear? Okay. Which of the following can be a tentative value of wing loading during takeoff? Given takeoff parameter is 130, power loading is 1 by 7.5. For a propeller driven aircraft, the takeoff parameter, the equation will be modified to incorporate power loading, not thrust loading, it will be power loading. That's the only difference. So takeoff parameter, the equation is directly given. You have a direct equation. Can you just substitute the values and tell me? I think one of the previous questions had takeoff parameter. So just use that equation. Instead of thrust loading, use power loading. Can you do it? Just use the takeoff parameter equation. Takeoff parameter equation was W upon S directly proportional to wing loading, and you had the sigma, you had CL takeoff, you had, it was thrust loading, you can just use power loading here. So it will be HP. Just erase that. Okay, so this is the equation. Can you just substitute the values and try to find out? It is not very straightforward, but you can just try doing this. Just take a few minutes and do this. We'll solve it together. This is the equation. Okay, so this is what you need to use to find wing loading. So what is wing loading? Wing loading is takeoff parameter into sigma into CL takeoff into power loading. So you have this, you have this, you have power loading, you need to find out CL takeoff. That is the catch here. Try doing it. And then we'll do it together. Just try doing it. The option B. Has anybody else gotten any other answer? Just try doing it. Can you tell us how you got option B? Okay, let me just take another sheet and write this down again. So W by S is takeoff parameter into sigma into CL takeoff into HP upon W. So we need to find out CL takeoff. So how did you find out CL takeoff? CL takeoff is CL max by 1.21. Okay. Yeah, so we just do that. We stall and we take off is CL takeoff by CL max. Okay, where we take off is 1.1 V stall. So if you take the square, it comes to 1.21. So now if you just substitute all the values, you get CL takeoff is CL max into V stall by V takeoff square. So you get CL max is 1.4 into, there's a factor there, 0.9 to 25 by 1.1 into 25 square, and you get around 1.04. Now you plug that into this equation and you should be able to find out the value. Okay, so takeoff parameter was 130. Sigma was 1. Takeoff is 1.04. Power loading is 1 by 7.5. You substitute option B, correct? So it's around 18. 18.03. So yes, option 2, correct. Then what will be the climb gradient given the climb velocity? Climb gradient, again, direct formula is there, right? What is the formula for climb gradient? G. G is just go over your notes. So it was D by W minus D by W, right? So this is nothing but, how is it? It's T minus D by W. It's related to rate of climb. So you have rate of climb by velocity of climb. Can you try finding out now? What will be G? Rate of climb is given to you, velocity of climb is given to you. What is the value? Why aren't the others trying? This is a direct formula, right? You can just substitute this and tell me. This was very simple. Be okay. Can someone else tell me what are the values? What is rate of climb? What is rate of climb? It's given in the question. Can you just tell me? Somebody else. I hope I'm audible to everyone. What is the rate of climb? It's given in the question. Can one of you tell me what the rate of climb is? It's just given in the question, right? Just tell me the number. By velocity of climb is directly given here. I hope you are following what I'm saying. 35.96. The value is 0.212. You're right, option B. Okay, next is what will be the flight path angle? Now you have the rate of climb, you have velocity of climb. What is the flight path angle? Formula is very simple, right? So sine gamma is the rate of climb by velocity of climb. So what is gamma? Just plug in the values. Gamma is sine inverse of the previous value. So that's just 7.62 by 35.6. Angle is 12.23. Correct. So that's that. Next, what will be the thrust loading during climb? Now, thrust loading for a propeller-driven aircraft, you have the direct formula. Do you remember that? Thrust loading. Just go over your notes, find out the value. You just directly substitute the values and you get it. Okay? You can just ignore that it's given in feet per second. Just get the value. It's a direct formula for a propeller-driven aircraft. Okay? Just go over your notes and tell me what it is. Just direct formula, just substitute the values and just tell me the answer. You get the formula, it's a direct formula for the propeller-driven aircraft. What is the formula? And you just have to substitute the values. It's a very straightforward question. So it is power loading, HP by W into efficiency. And there is a factor of 550.497. Okay, let's see if we're getting that value. 550 by VC. So power loading is 1 by 7.5. Theta is 0.8. 550 by VC. VC is 117.99. Okay, so 0.497. Okay, is anybody else getting another answer? Okay, so 0.497. So let me know if we're going wrong somewhere. We can always get back to it. And let me know if you're getting a different answer. We can see. Okay. Next question. I think this is the last in the series. What will be the maximum wing loading during climb in pound per feet square? Okay, so just keep the units in mind. So you just need to convert this into feet per second. So that value is given here. Okay, so you just have to do that 117.99 feet per second. Okay, so that just keep the units in mind. So this is the only difference. What will be the maximum wing loading during climb? How do we do this? So there was a relation that's limited, the limiting or the inequality related to the wing loading, right? There was an equation for that. Do you remember that? So wing loading is less than or equal to some term. Try using that equation. Do you remember the equation? Let's just write it down. Yes. So wing loading is less than or equal to, first was thrust loading minus G plus or minus under root of thrust loading minus G square minus 4 CD naught by pi E AR by denominator was 2 upon Q pi E AR. Now, all of these terms are given to you in your question. So let's just calculate it one by one. Can you try doing this? Just take a couple of minutes, try doing this, and then we'll solve this. Just try doing it. all of these terms are known to us. Okay, so this thrust loading we have just found in the previous question. So thrust loading was 0.497. G, again we have found 0.212. So just find out these values and you'll be able to do it. Look at the question if you want. Yeah, so these are the quantities. You might need CD naught and aspect ratio. Use them in the equation and tell me what will be the answer. What is the maximum wing loading during climb? You will need to use CD naught, aspect ratio, Ostwald's efficiency factor. Yeah, that's about it. And just make sure your climb velocity is 117.9 feet per second square. Okay, so it's given in meter per second, but the answer is required to be found in pound per feet square. Okay, this Q is your, you need to use this also. Q is your dynamic pressure. Okay, half rho v square, that's Q. Just find out individual quantities first, then substitute in the equation, it will make it easier. I hope you've seen the equation. I hope you remember this. This is the equation. Just find out each individual term and then you'll be able to do it. Let's just try doing this. So just quickly find out thrust loading minus G is 0.497 minus 0.212 around 4.285. So that is one term. Then let's do that for CD naught by pi PAR. So 4 CD naught is 0.02. Pi E is 0.8. Aspect ratio is 6. What is this value? Can you just calculate and tell me? What is that value? Let me calculate. Become 0.0053. Just let me know if I'm going wrong somewhere. Okay, so next term is 2 by Q by E A R. So this 2 by Q is 16. By E is 0.8. Aspect ratio is 6. What is this value? Zero 0.0083. Now just plug it into the main equation. So W upon S is less than or equal to, just plug all of them in, you get 0.285 plus or minus square root of 285 squared minus 0.0053 by 0.0083. It's less than or equal to. And they've asked you, the question says maximum wing loading, right? So you can just take the positive quantity, just take the summation, don't take the negative. So you just take the positive quantity. So it's less than or equal to. They've asked you for maximum. So you take the maximum, you take the positive one. Don't include the negative one. So what will it be? Find out the value 67.54. 67.54. What are the units? Pound per feet square. So yeah, so that is the maximum wing loading during climb. Okay, so I think with this we've come to the end of the series of this question. So we saw what all did we see what all we calculate for this data. First we saw tentative wing loading during stall, then wing loading during takeoff, then takeoff parameter. That equation was used to find out this. Then we found out the climb gradient and the climb angle, the flight path angle or climb angle, then thrust during climb, thrust loading during climb, and then the maximum wing loading during climb. Okay, so this can be the type of question that you can expect to solve. Like given a set of conditions, what and all can you calculate with it? Okay, so now this is something that we've been discussing for a while now. So it's a neutral point calculation. All right, so let's try doing this. First, we'll find the XNP, that is the equation in terms of XNP. Then we'll find out the numerical values and then we'll get the final neutral point. Okay, so let's just take a reference. So given this is the reference, let's take this as the reference. Okay, so I think I have slide. Yeah, so if this is the reference point, this value is XAC wing. That is the distance from the reference point, leading edge of the wing to the aerodynamic center of the wing. Then you have XCG, you have XNP, which we need to calculate. Then you have XAC tail and XAC canard. Before that, let's just look at the diagram that was given here. So from what is given to you in this table, okay, I think something is missing. Taper axis, yes. Taper axis. Okay, let's just say this is mid chord. This is trailing edge. And the last one. Okay. Now, given the taper ratio and the taper axis, what is the shape of the wing? Okay, the wing might be a little difficult to get. What is the shape of the canard, given the taper ratio and the taper axis? What is the shape of the canard? Triangular, yes. And what about tail? taper ratio is 1. So what is the shape of the tail? Rectangular, correct. And hence it does not have any taper axis. Okay. So both canard and tail are what kinds of airfoils? What kind of airfoil is the wing? Look at the data that is given to you. What kind of airfoil is the wing? What type of airfoil? Positive camber, exactly. What about canard and tail? Canard? Symmetric. So your CMAC value, this is empty here. What is CMAC? Both canard and tail are symmetric. So what is the CMAC value? 0. Perfect. Okay. Now let's move on and try to find out this X bar NP. Okay. So this quantity is what we need to find out. Let's try doing it. We'll start like we did in the previous case. We'll start with the equations. Okay. Right. So equation is moment about CG. What is the equation? mCg. Now what and all terms will come here? Let's start with the wing because that's what we are most comfortable with. So what will be the moment at CG due to, let's call this wing 1, let's call this wing 2. Okay. So what will be the moment at CG due to wing 1? If it's difficult to type down, you can also unmute and tell me. Either one is fine. So what will be the moment at CG due to wing 1? Let's concentrate on the lift first. So lift on wing 1, lift is the force, and what is the distance? So force into the moment arm, right? So what is the moment arm here? So this force into this distance. What is that distance? W1 xcg minus xac wing. Perfect, yes. Xcg minus xac wing. And now if both the lifts or both the wings have the same airfoil, you can just directly take this as 2. Okay. Then what about the drag? Does the drag contribute towards some moment at the CG? If I consider this distance as ZCG and this distance also as ZCG. Stick. So I can write dW1 into ZCG and minus dW. So if both the airfoils are the same, it will be just dW1 into ZCG, and both these terms will get cancelled out, right? If it's the same airfoil, considering that. Okay, so now the lift contribution is done. Next, tail. So what is the tail contribution? You have minus LT, and the distance will be, that is XAC tail minus XCG. Now, what is the contribution of the canard in the similar fashion? Prior to that, since your since your wings are positively cambered, you have moments. So you have 2 moments here, 2 MAC wing. Okay, so that will also be added up. They are not symmetric airfoils, so they do have moment about the aerodynamic center. that will be added at the CG. So you have 2 MACW. Okay. Okay. Now the contribution of the canard. Canard and tail are both symmetric airfoils, so there is no moment at the aerodynamic center. So what is the contribution of the canard at the CG? It will just be lift into this entire distance. What is that distance? Oops. This distance. What will it be? Okay. V plus LC into XACC plus XCG. Perfect. XACC plus XCG. Okay. So now how do we move on? What is the next step? Like in the previous case, we had done for the simple lift, wing and tail contribution. What do we do next? How do you find out what is the next step towards finding out neutral point? You have the moment about CG. We should non-dimensionalize it, right? So divide throughout by half rho V square SC bar. So divide throughout by half rho V square SC bar. Okay. So now if you divide on the right hand side, on the left hand side, you will have CM. CMCG, we'll call it as CM. On the right hand side, you will have lift on wing 1 divided by half rho V square SC bar. Now this, it will give you CL of the wing by C bar, correct? And CL of the wing is CL naught of the wing plus CL alpha of the wing into alpha of the wing by C bar. Okay, so now let's write the equation. So it will be CMCG or CM is 2 CL naught of the wing plus CL alpha of the wing into alpha of the wing into that C bar. I'm taking it to the other side. So it will be XCG minus XAC wing by C bar. Okay. Similarly, for the tail, let's do it for the tail now. So it will be minus CL naught of the tail is, okay, let's just write it for continuity here. CL naught of the tail plus CL alpha of the tail into alpha of the tail. And you have XAC tail minus XCG by C bar. Now, this is straightforward. So you have, what is this value here? 2 CM AC wing. Then you have plus CL naught of the canard plus CL alpha of the canard into alpha of the canard into XACC plus XCG by C bar. Okay. Now before we proceed, we need to expand alpha tail and alpha canard. Both of them have terms that are dependent on alpha wing, right? So what is alpha tail? Similar to the previous case, we'll just take alpha wing plus I tail. We should have a minus downwash. We'll ignore it for now, okay? We'll just take it to be 0. Alpha of the canard is alpha of the wing plus IC. Okay, that's the tail setting angle, canard setting angle. Okay, so now let's just substitute these. What do we get? So CM is CM naught plus CM alpha of the wing into alpha of the wing. So let's just write down terms that are dependent on angle of attack of the wing and terms that are independent. Okay, it will simplify our process. So let's write CM naught. What terms are independent of angle of attack on the wing? What are those terms? Let me take another color. Okay. So this, and this, correct? So let's just write it down. So it will be 2, okay. CL naught of the tail and CL naught of canard are 0 because they are symmetric airfoils, right? So you have 2Cl naught of the wing XCG minus XAC wing. Okay, let's just represent, okay, C bar. Then you don't have Cl naught of tail, you don't have Cl naught of canard, you have a plus 2 CMAC wing. Is that all? Am I missing something? It's all right. No other terms are missing. Have I made a mistake? Okay, here you're dividing it by S, so you will have terms. You will have here, you will have ST upon S. Here you will have SC upon S. Correct? Just correct me if I'm going wrong anywhere. This was a mistake. Correct me if I'm going wrong anywhere, okay? All right. So Cm naught is this quantity. Now let's find out Cm alpha. Okay. So Cm alpha, let me just write on the equation again. Or we'll have to go back and forth. Okay, let's just do that. So Cm alpha. What is the first term? Let's take another color. So Cm alpha, we'll have this. We'll have this. We'll have this. Correct? Correct? Okay, have I missed some term in Cm naught? Have I missed some terms in Cm naught? Just look at it carefully. I have missed some terms in Cm naught. Can you tell me which are those? Terms that are independent of angle of attack of the wing. Can you tell me what those terms are? What is missing in Cm naught? So let me write it down, see if it makes sense. Plus Cl alpha tail into I tail into X AC tail minus XCG by C bar into ST upon S plus minus plus Cl alpha canard IC XACC plus XCG by C bar into SC upon S. Yes, this is the complete Cm naught. Is it right? Am I missing some more terms or is this incorrect? Let me know. Just look at it and tell me if the Cm naught is incorrect. So all the terms that are independent of angle of attack of the wing, alpha wing, right? So there were these terms that are independent. Is there some mistake now? Just look at it, look at Cm naught, try deriving it on your own. Tell me if it's wrong. Tell me if I'm still missing some terms or if some terms are extra. Or tell me if it's correct. Okay, it's correct, fine. All right, now let's go on to Cm alpha. So you have 2 Cl alpha of the wing into XCG minus C wing on C bar. Then what do you have? Cl alpha of the tail. Then you have minus Cl alpha tail XAC tail minus XCG by C bar into ST upon S plus similarly for the canard, CL alpha canard XACC plus XCG by C bar SC upon S. Again, are we missing any terms? Is this correct? Are we missing any terms? Just look at it. I think it's fine. We are not missing any terms. This is correct. Okay. Now, how do you find out X and P? Now you have this equation. How do we find out X and P? We need to find out the equation for neutral point. How do we find that out? What is the next step? What is the next step towards finding out the equation for neutral point? We did this in the previous derivation, right? Making CM alpha 0. Correct. So at CG equal to neutral point, your CM alpha is 0. So just substitute everywhere where there is CG, put X and P in this equation. So and CM alpha is 0. What do you get? 0 equals 2 CL alpha wing. You get X and P minus XAC wing by C bar minus CL alpha tail XAC tail minus XNP by C bar plus CL alpha chamber canard XACC plus XNP by C bar. There is a P upon S, C upon S. Okay. So now this from this equation, we will be able to find out X and P, right? We need to find out X and P. Okay. So now let's look at all the terms. What and all we need to find out. Okay, let's just write it down. Let's list it. We need CL alpha wing. We need CL alpha tail. We need CL alpha canard. Then you need XAC wing. You need XAC tail. You need XACC. Anything else? Yes, you need S. You need S tail. You need S canard. You also need mean aerodynamic chord of the wing. Anything else? All the other terms we know. Now from the table that is given to you, so you have CL alpha of the wing, canard, and tail. So you have this. Do you have XAC wing? Do you have that quantity? Let's look at the figure that is given to us. What values do we have? We have 1.5 meters here. So let me just try to, yeah. So what do we have? We have, this is 1.5 meters, this distance. Correct? How do we find out XAC wing, XACC, XAC tail? How do we find out? Let's start with the canard. Also, yeah, this is another thing. The values given here are for 2D. Okay, we need to convert it to 3D. That is also there. Okay, so let's start with canard. We'll do it for each surface, okay, for the canard. Let's start with the canard. So now what do we need? You need SC. What is the area of the canard? Now from the table, we know that the canard was triangular, right? So it was triangular where the span was 1 meter, root chord was 0.5 meter. So this is 0.5 meter. Span is, what was the span? 1 meter. Okay, they're not given units, but 1 meter. All right. Okay, so now what is the area of the canard? SC. What is the formula? It's just area of the triangle, right? Half base span of the canard into CR, root chord. So that is half into 1 into 0.5, right? So that is 0.25. So we got one value. So SC, this is done. Next, what do we need to find out? Then you need CL alpha C. CL alpha C 3D. Correct? That is CL alpha 2D by, do you remember this relation between 3D and 2D? 1 plus CL alpha 2D by pi E AR. Is the aspect ratio given in the question? No, E is given. E is 0.8. So E is 0.8. How do we find out aspect ratio? What is aspect ratio? B square by S. Correct? B here is 1. Are you following what I'm doing? Just stop me at any point if it's confusing, all right? So S, here it's SC. It's all for the canard. SC we've just found out is 0.25. So what is the aspect ratio? What is this value? 1 by 0.25? 4, right? Aspect ratio is 4. So just substitute the values. CL alpha canard is 5. So 5 by 1 plus 5 by 5 into 0.8 into 4. What is this value? CL alpha 3D. What is this value? Just calculate and tell me. Three point three. Okay, so 3.34. So we have found out this. Let me just erase this. Yeah, so we just found out CL alpha C, SC. Next is XACC. Okay, let's try doing that. Prior to that, you need mean aerodynamic chord. What was the formula? The empirical relation. You had 2 by 3 root chord, 1 plus taper ratio squared plus 1 plus taper ratio. Correct? Yes. Here taper ratio is 0. So what is the value here? It's just 2 by 3 into 0.5, which is 0.33. Okay. Now, how do you find out XACC from the leading edge? Let's just do it from here. So if this is your mean aerodynamic chord, this is 0.33. What is the location for aerodynamic chord? Aerodynamic center. This is AC. How do you find out? Okay, let's take another color. So we need to find out this distance in blue, which is XACC. How do you find that out? It is this orange distance plus this green distance, right? So what is the distance in orange? I'll just write it down. Tell me if I'm right. Okay. So CRC minus C bar C. The distance in orange. Is that right? Is the distance in orange right? CR, that is a root chord, minus C bar. Is that correct? Yes. Okay. Now the distance in green. What is the distance in green? What is the distance in green? Exactly. CC by 4. Correct. Perfect. Can you tell me the value now? CRC is 0.5. CC is 0.33. And this is 0.33 by 4. So what is this value? 1.75 meters. Okay. Just tell me if I'm making a mistake somewhere. Okay. Oh, this is not 1.7. This is 2.5. Correct? 0.25. 0.25. Sorry, my bad. 0.25. So now, what is XACC? This is XAC. Let's just call it something else. XAC prime. Okay. What is XACC? This distance is XACC, right? What we've gotten now is this is 0.25. How do you find out XACC? Can you tell me? So distance from the leading edge of the canard to the aerodynamic center of the canard is 0.25 C. Correct. Now we need to find out this small blue distance. So it's 1.5 plus the blue distance. Correct? So it is equal to 1.5 plus the distance in blue. What is the distance in blue? It's just the root chord minus this value, right? So it's just 0.5 minus 0.25. Let's take a minute to process this. The distance in blue is just the root chord. It is CRC minus 0.25. Yes? Is that correct? I know this may be a little confusing, but just try to understand it. Exactly. So 1.75 is the final answer here. So we have found out the area of the canard, the CL alpha of the canard, and the XACC. So this one. Okay, so we've completed all the requirements for the canard. Now let's move to the next structure. Okay, I hope it's clear. Let's go on to tail. Let's take tail. Yeah, so S tail. So tail was a rectangle, right? Because taper ratio was 1. So it's just CR tail into B tail. That is the area. So what was the root chord was 0.5 or 0.3 and span was 1.5. So it's 3 into 1.5, which is 0.45. So we've got area of the tail. So this is done. Next, CL alpha of the tail. Before that, what do we need? We need aspect ratio. Aspect ratio of the tail is B square upon S is T. T. Span is 1.5 square. Area is 0.45. So what is this value? It's 5, right? Aspect ratio is 5. So now let's do CL alpha 3D of the tail. What is the value? 4 by 1 plus 4 by pi is 0.7 into aspect ratio is 5. So this value comes to 2.9. So we found out this term also. Stop me if it's confusing or if I'm going wrong anywhere, okay? Next, we need to find out XAC tail. XAC tail. It is a triangular wing, so it's just C bar by 4, right? This distance is just C tail by 4. What is C bar? What is the value for C bar? Equation was C tail bar. It's a rectangular wing. So what is the C bar? It's a rectangular wing. So what is C bar? C bar of the tail is mean aerodynamic chord of the tail is the rectangular wing, right? So it's throughout it's the same thing. It is the CR, which is nothing but 0.3. Correct? So what is XAC tail? What is XAC tail? Look at what is given to you in the question. Have this distance 0.5 and you have span of the wing is 4. Correct? So you have 4 plus 0.5. Where will be? Okay, there is. Okay. So you have, where do I draw this? So you have, this is 4. This is 0.5. And this small quantity is 0.3 by 4. So it is just 4 plus 0.5 plus 0.3 by 4. Yes? Is this clear? I know it's slightly confusing, but are you able to follow this? XAC tail. The 4 and the 0.5 are given to you in the question. 4 is the span of the wing. Oh, it's the mean aerodynamic chord. We can't take the span. Okay, that's my bad. Mean aerodynamic chord of the wing. How do we do this? That is not 4. You can take it to be the root chord, okay? So this distance is the root chord is 1. Sorry about that, it's 1. Okay, is this clear? So root chord of the wing plus that 0.5 is given to you in the question, plus that 0.3 by 4. 0.3 is the mean aerodynamic chord of the tail. Since it's the rectangular tail, the root chord, tip chord, mean aerodynamic chord, they're all the same. Correct? So what is this value? 4 plus 0.5 plus 0.3 by 4. 4 plus 0.5. 4.575. 4.575 meters. Okay, so you have this also. You've gotten XAC tail. Now let's look at the wing. Now that we have done for the canard and the tail, will you be able to do it for the wing? What do we have to find out? We have to find out S of the wing. Then you have to find out CL alpha of the wing. Then you have to find, so for that you need to find out aspect ratio of the wing. Then XAC wing. Will you be able to find out these terms for the wing given the value in the question? And then we'll discuss this next week, okay? Then we'll find out the final neutral point value. Just go over what we did for canard and tail. It should be easier for the wing because it's just from the leading edge of the wing. That is your reference point. Okay? Okay, try doing this and we'll complete this question next week. Okay, are there any questions? Do you have any questions from this session? Do you have any questions from the session? If not, we'll end the session here. All the very best for your assignment. We'll meet again on Tuesday. That time we'll complete this question and deal with the other questions. All right. Thank you. Thank you.